This is a database problem in that a table is given with selected values of f prime. They also tell us that f is twice differentiable, just meaning that the derivative exists and the second derivative exists. Also meaning that the derivative, if the second derivative exists, then the derivative is a continuous function. Part A asks us to write the equation of the tangent line at x equals 1. So if we're going to write the equation of a tangent, then point slope at x equals 1, the y-coordinate is given, it's 15. The slope is given in the table at x equals 1, it's 8. Y equals the slope times x minus the x plus the y. And then they ask us to use this line to approximate f of 1.4. So then f of 1.4 is approximately 8 times 1.4 minus 1 plus 15. No need to simplify since this is free response. This question also is non-calculator. So then we don't have that option to simplify. So then leaving the answer in this form and then moving on to the next part of the problem. Part B is saying use a midpoint Riemann sum with two subintervals of equal length to approximate this integral. So integral from 1 to 1.4 for f prime of x dx. When I see this integral of f prime, then it does make me think first fundamental theorem. So this integral should be equal to f of 1.4 minus f of 1. F of 1 is given. F of 1.4 is what we're going to end up approximating. But then I don't have a function to integrate, so that's why we're using a midpoint Riemann sum, two equal subintervals. So that means from 1 to 1.2 and 1.2 to 1.4 is going to be the approximate value of this integral. So two midpoint rectangles, base times height plus base times height. Both bases are going to be 0.2. The height is determined by the y value at the midpoint. For the first rectangle, that's 10. For the second rectangle, that's 13. And then it says, use this approximation to estimate the value of f of 1.4. So f of 1.4 minus f of 1, applying the first fundamental theorem, 0.2 times 10 is 2. 0.2 times 13 is 2.6. When I integrate f prime, I get f, and then when I plug in the upper limit, I plug in the lower limit. That's where I get f of 1.4 minus f of 1. If I want to approximate the value then of f of 1.4, it's going to be approximately 2 plus 2.6 plus the value of f of 1. The value of f of 1 is given. It's that 15 that we used in part A. Approximately 2 plus 2.6 plus 15. I didn't have to simplify. I didn't have to multiply the 0.2 times 10 and the 0.2 times 13. But I did just to have less writing here. And then part C, using Euler's method, starting at x equals 1 with two steps of equal size. So starting at x equals 1, trying to get to 1.4, two steps of equal size. That means we're going to recalculate at 1.2 our tangent line. Since this is Euler's method and this is tangent line approximations, so then starting at 1, where the y value is 15 and the slope is 8, then we're going to recalculate at 1.2 and then again at 1.4. Our tangent line, 8, the slope times x minus the x coordinate, which is 1, plus the y coordinate is 15, and then we're going to plug in 0.2 to get the new y coordinate. When I plug in 1.2, 8 times 0.2 plus 15, 8 times 0.2 is 1.6, 1.6 plus 15 is 16.6. 16.6, and then I want the slope at 1.2. At 1.2 from the table, the slope tells us, that the slope is 12. The new tangent line, y equals the slope times x minus the x coordinate plus the y coordinate. And then we're to our last step, just trying to approximate f of 1.4. So then just plugging in 1.4 for x, no need to simplify. This is our final answer then for part C. And then for part D, write the second degree Taylor polynomial for f about x equals 1. And then we're going to use that Taylor polynomial to approximate f of 1.4. They told us the degree, so the largest exponent should be a 2. The general form for a second degree Taylor polynomial. And this is centered about x equals 1. It's going to be f of 1 plus the first derivative at 1 over 1 factorial x minus 1 to the first power. First derivative at the center over 1 factorial times x minus the center to the first power plus the second derivative at the center over 2 factorial x minus the center to the second power. And this is the Taylor polynomial, which we're using to approximate f. And we want to use it to approximate f at 1.4. We're going to fill in the values for f of 1, f prime of 1, and f double prime of 1. F of 1 is 15. F prime of 1 is 8. We can read that from the table. F double prime at 1 is 20. It's given. And then x minus 1 to the second power. Here's our Taylor polynomial that's approximating f of x. And then f of 1.4, just plugging in 1.4 for all the x's. So f of 1.4 is approximately 15 plus 8 times 0.4 plus 10 times 0.4 squared. And I don't have to simplify. I simplified a little bit on that last step, but I don't have to do any of that simplification. The points here, first point came from writing the equation of the tangent line. The second point came from using the equation of that tangent line to approximate f of 1.4. A point for writing the midpoint Riemann sum. 1 point for recognizing that we had to use the fundamental theorem, the first fundamental theorem of calculus, to get f of 1.4 minus f of 1, and then that final answer, which is our approximation for f of 1.4. 1 point for using Euler's method. So just showing that we knew how to use Euler's method was a point. And then that final approximation for f of 1.4 from Euler's method was another point. 1 point for writing the Taylor polynomial, and 1 point for using that Taylor polynomial to approximate f of 1.4.